Ezra. I'd like to thank the organizers for having me invited me to speak here. So the work I'm going to be talking about today is part of a much bigger project that I'm working on with Bill Dwyer. I've been working on for the last few years. And this construction I'm going to be talking about today is actually something that came up in the process of wanting to construct a model for derived mapping spaces of operad maps of different types. And somehow this construction I'm going to talk about today was supposed to give us a tool for doing a kind of inductive argument in this context. It turns out we found a completely different proof that doesn't use this construction, but fortunately this construction is useful for other things, so it wasn't a complete waste of time. In any case, it's a sort of a pretty exercise, and I hope I'll be able to convince you that it's worth thinking about. So let me set up the framework. So there haven't been really so far any sort of serious operad talks in this conference, even though it has operads in the title. So let me just write down a little bit of notation, set up the framework properly. So I'm going to be working in the following framework. So I'm going to be looking at a category of symmetric sequences of either topological spaces or simplicial sets. It's often more convenient to think about simplicial sets. Sometimes you might need to have topological spaces. Then this is a monoidal category with respect to several different monoidal products, in particular with respect to the composition product or the plethism product, which is this asymmetric, non-symmetric product, which I'll denote like this, circle. And then it has a unit object, G, J. Keep track of what language I'm speaking here. And so this is going to be the category that's underlying everything, this category of symmetric sequences of either topological spaces or simplicial sets. And then within this category, the monoids here, those are operads, the monoids in this category. So the operads I'm usually going to note either P or Q or something like that. So it's a symmetric sequence with a multiplication and a unit with respect to this composition monoidal structure. And then if I have two operads, P and Q, I'm going to be interested in looking at PQ bimodules with respect to this composition structure. So if P and Q are operads, then I can think about PQ bimodules, and bimodules in this context here. So this is going to be some sort of symmetric sequence M equipped with a left action of P and a right action of Q. So it's M circle Q to M. And because of the asymmetry of this composition product, left and right module structures are very, very different for these symmetric sequences. So as examples, I'll just mention these. If you want to see more examples, I gave an hour and 15-minute long talk on bimodules of operads at the introductory workshop in January, which is actually online. But let me just mention briefly. So if you have, for example, any P algebra, where P is an operad, then you can make it into a left P module by sticking that algebra into arity 0 and having the trivial object everywhere above that. Another example, if your operad you're interested in is the associative operad, and you think about, well, what does it mean for something to be a left module over the associative operad? That just means it's exactly a graded monoid. So left modules are not that strange. It's really algebras, graded monoids, things like that. Right modules are a little more obscure. If you start with something that's a coalgebra over some operad, then you can make a symmetric sequence. So if you have some object C, which is a P coalgebra, then you can make a symmetric sequence starting with iterated powers of this object C, looks like a tensor algebra. Then this thing is actually going to be a left module of the associative operad, because it's a graded monoid, and a right module over your other operad. So these things show up very naturally, these sort of bimodules. And I'm going to talk about, when I talk about a couple of applications of the construction that Bill and I gave, I'll give some more examples, some more geometric examples of bimodules. So we're going to be interested in categories of these things. So when I write up, it's going to be...
Sorry. When you're saying create monad, you mean, in that case, you mean the non-symmetric?
Yeah, okay, we'll forget the... roughly. Okay, so let's let this is going to be our category of operads. All operads in our category. And then I'm going to make a category over that one, which is the category of all bimodules. All, and let's call these operatic bimodules to keep in track of the fact that we're really using this asymmetric composition structure. So of all operatic bimodules. So what do I mean by that? An object in this category is going to be, well, a bimodule, obviously. So an object here is going to be something, so M is going to be a PQ bimodule for some operad P and some operad Q. And if I want to think about what morphisms are in this category, then so if M is a PQ bimodule and M prime is a P prime Q prime bimodule, then a morphism from M to M prime is given by a pair of morphisms of operads, one from P to P prime, one from Q to Q prime, and then a morphism of PQ bimodules from M to M prime seen as a PQ bimodule. So a morphism from M to M prime consists of operad morphisms, phi and psi, plus, let's call it F, a PQ bimodule morphism. So I'm going to use phi and psi to pull back the P prime Q prime bimodule structure on M prime to a PQ bimodule structure. So I'll write it like this. Of PQ bimodules. So I have this kind of structure here. Now there's an obvious functor from the category of bimodules to the category of operads across operads. Pi. From this category of bimodules to operads cross operads, that of course just takes a PQ bimodule, you write it like this, to PQ, and then it's going to take the triple F phi psi to phi psi. Okay, so sort of thing one often looks at when one's thinking about categories of bimodules and so on. And there's also, this thing has a section. So if it's a section, it's called gamma. So from up, cross up to bimod, it's just going to take a pair of operads and send it to the free PQ bimodule operad on a symmetric sequence that just has one generator and arity 1. Another way to write that is simply as P circle Q, which is a left P module and a right Q module. So we can also think of that as P circle, and then I have little sequence concentrated in arity 1, circle Q. So getting a free PQ bimodule like this. And then obviously, pi composed with gamma is just going to be the identity. Okay, so I said I want to talk about the Boardman-Vogt tensor product, a Boardman-Vogt tensor product in any case, for these operatic bimodules. So I need to tell you about the usual Boardman-Vogt tensor product of operads first. So let's just do that. So the Boardman-Vogt tensor product in its usual version endows the category of operads with a symmetric monoidal structure. So it's a functor will denote like this. Like so. And what's special about it is it gives us endows this category of operads with a symmetric monoidal, even closed symmetric monoidal structure. And why would one be interested? I mean, it's always nice to have a monoidal structure, but what is sort of the algebraic point behind having this Boardman-Vogt tensor product? It's that, well, you say, if I have two operads P and Q, what does a P tensor Q algebra look like? Well, a P tensor Q algebra, it's a P algebra in the category of Q algebras, or a Q algebra in the category of P algebras. So it's an object, a symmetric simplicial set or topological space, with commuting P and Q algebra structures. There's a P algebra in the category of Q algebras, or it's a Q algebra in the category of P algebras. So it's a way of codifying these sorts of commuting structures, commuting algebra structures. So let me say something about the possible geometric meaning or topological interest of this Boardman-Vogt tensor product in a couple of examples. So the first example, this is work of Dunn from 1988. Let Cn be the little n cubes operad. So let Cn okay. So Dunn showed that if you take the little 1 cubes operad, little intervals operad, and you iterate the Boardman-Vogt tensor product k times, then what you end up with is in fact weakly equivalent to the little k cubes operad. So this has a nice geometric sense. And in fact, I believe this is what Boris was talking about yesterday in his talk. He mentioned taking these tensor products of operads. So that's a very special case working with these little n cubes operads. And then Mortenbrunn, Fedorovitz, and Vogt in 2007, they proved something related, which is that if I take the associative operad and I take its Boardman-Vogt tensor product with the little n cubes operad, little k cubes, let's say, then that one is in fact weakly equivalent to little k plus 1 cubes operad. And this is true for all k. And then finally, in 2011, Fedorovitz and Vogt, 2011, said that if you have, well, let's first define what we mean by an En operad. An En operad in this context is going to be any operad that is weakly equivalent to the n cubes operad. So what they showed is that if I have Em and En, which are cofibrant in some appropriate sense, and the covibrancy is very important, as I will mention in a moment. If these guys are cofibrant and Em is equivalent to Cn, like this, if now I take the Boardman-Vogt tensor product of Em and En, it will in fact be equivalent to Em plus n. Then Em n So this Boardman-Vogt tensor product works together very nicely with these sorts of functions.
Cm plus n.
Cm plus n, thank you. Because I hadn't defined em plus n.
Right, that's why I said.
Thanks, Ezra. Okay. This is the one for short people. There we go. Okay. So, just to point out how important this cofibrancy condition is here, let me just all kinds of bad things happen when your opereds are not cofibrant. Be very, very careful. So, turns out that if you take the associative operad, which is not cofibrant, you tensor it with itself, then you get the same thing as if you took the associative operad and you tensored it with the commutative operad. And everything just collapses down to nothing, and all that's left is commutative. So you really have to be careful. This cofibrancy condition is essential.
Cofibrancy is a symmetric sequence, or cofibrancy is an operad?
It's a symmetric sequence.
No, as an
Or it's operad?
As an operad? Because us is cofibrant.
That's true. Yeah, okay. But there's a condition about the symmetric. Yeah. Yeah, thank you.
Excuse me.
Okay.
A little confused here. Isn't com the unit and not the zero with respect to the Boardman-Vogt tensor product?
No. This is.
But it was the com was the unit with respect to Boardman-Vogt.
No, it collapses everything.
For the arity-wise tensor product, if you want, but not for the arity-wise tensor product as a unit.
Yeah, but not. But this is the Boardman-Vogt.
This Boardman-Vogt tensor product is not another tensor.
Yeah, really.
Operad.
If you're having something in arity 0, when you're taking the Boardman-Vogt tensor product, just makes tons of stuff collapse. This is the problem. That's why com is not the unit with respect to
It's a
Boardman-Vogt.
zero.
Does tensor product take cofibrations to cofibrations?
Yes.
Thank you.
Who said that? Oh, this is an open problem.
Okay,
All right.
let's move on.
Let's move on. I don't know the answer. Clemens says that it's an open problem. Okay, I'm not here to talk about the actual Boardman-Vogt
It
tensor
is
product.
not known whether this is a monoidal model category, the category of operads. So the Pouchet product
Okay,
axiom
I
is
didn't
not
mean to
known,
ask that
otherwise
That's fine.
I apologize.
That's okay. Okay, so let me just formulate more audience participation. I'd like to formulate the main theorem. So, for something that what Bill and I wanted to do, we wanted to be able to sort of lift this Boardman-Vogt tensor product from the category of operads to the category of bimodules. Turns out we actually don't need to do that for what we were thinking about, but it's a fun exercise anyway. So what it says is the following thing, that let's consider the following picture, where here we have the category of bimodules. Here we can take pi cross pi. Here, this is going to be like the way you define multiplication in a tensor product of algebras. We'll come back to this. Bimod. So here we have pi, and we also have our sections going back up. Okay, so here I'm going to look at the map that takes a pair of pairs and maps it to the pair of tensor products. And the point is that there is a functor here, so that both of these diagrams commute. So that if you project down and do this, it's going like that, but also for the sections. So in particular, this means that if I look at, let's see, I'll put it here, commutes in both directions, up and down. Right, so in particular, this says that using the fact that it commutes with these section maps means that if you take the free PQ bimodule tensored with the free P prime Q prime bimodule, then it should be the free P tensor P prime Q tensor Q prime bimodule.
Catherine,
Yes?
in your diagram in the bottom right-hand corner, should that be op times 2?
Yes. Thank you. So that's one thing. And the other thing is that, so the other way it's commuting says that if I have M, which is a PQ bimodule, and M prime, which is a P prime Q prime bimodule, then this guy is a P tensor P prime Q tensor Q prime. So things sort of fit together the way you would like them to. Okay. So what I want to do today is to give you some idea of how we can prove this theorem, because I think some of the techniques that we apply in proving this theorem can be useful in other similar contexts, and to sketch a couple of applications of this tensor product. So because there's some interesting, when I talk about sketching the proof, there's some interesting techniques and sort of apparently new monodal structure and symmetric sequences. It shows up different kinds of things that are perhaps useful in other contexts. I think it's worth to go through the proof and then sketch one or two depending on the time. So I'll just say sketch a couple of applications. So I'm actually going to start with one of the applications because otherwise it's just going to seem like I'm playing some sort of abstract category theoretic game, which is fun, but maybe might seem kind of pointless to people who are not so interested in abstract category theoretic games, or just operads in particular. Although if you aren't interested in operads, I don't know why you're here this week. So here's the first application. Something about configuration spaces. So when I saw the program for this week, I thought, fantastic. John Francis is speaking before I am, so that I'll just be able to say factorization homology and everything's going to happen like by magic. So we're going to let M be a framed M manifold. Some trivialization of the tangent bundle. And I'm going to consider the following symmetric sequence. So if I have any L that is less than or equal to M, I want to consider the following symmetric sequence. I'll call DLM. So it's a symmetric sequence. So that in arity K, what I have is a space of framed embeddings from K copies of RL into M. This gives us a nice symmetric sequence, the permutation, you're commuting the factors, so the sum ends here for the permutation action. So this thing, in fact, has certain properties. So first, I'd like to note that, let's see. So why in the world did I talk about configuration spaces here? That this thing has the homotopy type of the configuration space of k points in M. All right, maybe I'll write like this. This is telling us that it has the right homotopy type for configuration spaces. On the other hand, if you look at dl of RL, they have the same dimensions here. So in this case, this thing actually turns out to be an operad. So it has natural operad structure. And in fact, is weakly equivalent to the little a, little l cubes operad. Little l cubes operad. So it's one of these EL operads, and I'm going to call it, in fact, EL to keep it simple. So the operad structure is just coming from the obvious sort of iterated composition using these coproducts. Okay.
Is EL or friend EL?
Sorry?
Is it E? It is.
It's EL and not EL framed. So it really is a little distant nod to cacti.
Can I ask an embarrassing question? Are there any embeddings of the empty set into M? Like, so when k is 0, is it empty or is it 1 point?
1 point.
It's 1 point. Okay. Oh.
But you consider that.
1 point.
It is, okay.
But just one.
Yeah, yeah. Well, there's only one point
Yeah.
in the set of
Right.
functions, so it's either an embedding or it isn't.
Yeah.
Yeah. It's also possible. Yeah.
Okay. And then the final point I want to make is that if I take any other n, then this guy is in fact a right module over EM. So we can look at it as a bimodule over the unit J on the left and EM on the right. So it's a right EL module. So we can think of it as a JEL bimodule. That's how this theory of bimodules sort of covers the theory of right and left modules as well. So that's how we fit into this complex of modules I was talking about. So let's see. What was I supposed to tell you? Right. So we're looking at this as a functor.
Did M and L get mixed up here a little bit?
I don't think so.
We don't want our L to be the same dimension as the manifold for this module structure.
No, because I'm definitely precomposing with L's. So the M has to be greater than or equal to L. Because if you think about where the right module structure is coming from, it's coming from doing a precomposition with a bunch of other submentions of our L.
Excellent, thank you.
Yeah. So it's an EL module for every L less than or equal to M.
Just the trivial one. Oh, is that I or?
That's with the J. Let's see, it's gone now.
It's a J.
It's the unit
Yeah.
of the composition product.
Yeah. Okay.
Okay.
The composition is not. It's identified.
So what I'm doing is I'm looking at this as a, now for any M greater than or equal to L, I'm looking at this as a functor from framed M manifolds into the category of right E modules or of JEM bimodules. So I'm going to think of it. Okay.
EL?
EL. Yes, thank you. There you go. All right. So why does one care about these things? The point is that these right EL modules capture a lot of the geometric structure of these manifolds. So there's a theorem which is due to work of Michael Weiss with his embedding calculus, and also to other work on calculus by Goodwillie and Klein. And they showed that if I have M and N, which are frame manifolds of dimensions n, little m and little n, these are frame manifolds such that the codimension, well, such that, let's see me get this right, n is greater than n plus 2, then the homotopy type of the embedding space, of the space of all embeddings, framed embeddings from M into N, we can capture this homotopy type by looking at the derived mapping space of right EM module maps from between the respective DLs there. So, sorry, it's the derived mapping space. I'll put a little H up there to minus its derived of, now it really is EM from DM. So this really captures a lot of the geometry of the space. So that's one, you can say this is sort of like motivation. To even think about these modules. Okay. So, what is it that Bill and I have done in this context with respect to this lifted Boardman-Vogt tensor product? So we have the following result. So it turns out that under these same conditions, if M and N are framed manifolds, then if we take the EM module that's associated to M, and we take the EN module that's associated to N, we can form their tilde tensor product. So tensor product is bimodules. And actually we're going to do this in a derived way, sort of left derived construction. Then this thing is actually equivalent as M plus N, EM plus N modules to DM plus N. N cross.
Wait a minute. Now I want to ask my question again. Does this tensor product take weak equivalences between cofibrant objects to weak equivalences, I guess? I mean, otherwise I'm not sure what you mean by derived.
Yes.
It does. Okay.
So this is as an EM plus N, or better said, so this is in some appropriate sort of infinity context. It's right EM plus EM plus N modules. So this is using the result from Fedorowicz and Vogt that I mentioned before, the fact that here, if I take a left-derived version of this, I get this. That's how I can even make sense of this. So the way this proof goes is that you say, aha, thanks to David Ayala and John Francis, we can play this game in the world of factorization homologies and look at this. Look at these functors as factorization homologies where the target symmetric monoidal infinity category or quasi-category is the category of right E modules with respect to the graded tensor product. The graded tensor product is a symmetric monoidal product on the category of right EM modules. So that's how this game is played. So and in fact, David and John did all the hard work and hero, because they proved that what we needed to be excisive was actually excisive, and then all we have to do is check that it works for Rm and Rn, and that's easy. So one just has to have the idea in that case. Okay, so that's, I think, one motivation for even thinking about this lifted Boardman-Vogt tensor product. So now I want to say a few words about how one can go about trying to prove this theorem. How can you figure out what this lift should look like so that you get compatibility with both the projection and with the section map? So there's the strategy. We know what we want this tensor product to be. We take the tensor product of two free bimodules, each just on one generator. So what do we want to get when we take the tensor product of any two free bimodules? So what you want to do is figure out how to complete the following equation. So now, just to emphasize that I'm actually working with bimodules and not just with symmetric sequences, I'm going to use notation for free bimodules. So if I have a free PQ bimodule on some symmetric sequence X, and I take its tensor product with a free P prime Q prime bimodule on some other symmetric sequence X prime, then, well, I want this thing to be, sort of left adjointy, and so it should also be free, right? That would fit with our picture of what happens when you have only one generator. So it should be free on P tensor P prime and Q tensor Q prime, but on what? What goes in there? But to figure out what goes in there, I need to remind you how the Boardman-Vogt tensor product is actually constructed. And that's what will motivate what we end up putting in there to replace the two question marks. So, here's the motivation. If I have P and Q, which are operads, then when I formulate Boardman-Vogt tensor products, I find in the following way. I'm going to take their coproduct as operads, and then quotient out by a certain relation, which basically says that I can pull any operation in P through an operation in Q. So the Boardman-Vogt tensor product here is the coproduct as operads. This is not disjoint union. This is a big, nasty, horrible, enormous operad here. Sorry. So it's a pretty big thing. But we're gonna make it a whole lot smaller because we're going to quotient out by something that allows us to pull certain operations to certain other operations. And this is when it's nice to use some colors. So, kind of thing I want to be able to do is say that if I have some operation P in P, and then I have the same operation hanging off so it's 3 times the same operation from Q. And let me just number the outputs like this. This operation in this coproduct here is going to be equivalent to the operation where I have Q, and then I hang P off it twice. And I change the ordering. 1, 3, 5, 2, 4, 6. There's a permutation of the inputs that has to come in. But there you go. Quotient that by this relation, and that gives you the Boardman-Vogt tensor product. And the equivalence class of this thing we call little p tensor little q.
But this is commutativity in the sense of algebraic theories?
In the sense of what, sorry?
In the sense of algebraic theories?
Yeah, I guess so. I'm not sure. But so the equivalence class of these guys I'm going to call P tensor Q. Now, one thing I'd like you to observe is that this gives us a certain operation on the Cartesian product of P and Q that looks as follows. The things in P of arity K crossed the things in Q of arity L into the things in P tensor Q of arity K times L. That takes PQ to P tensor Q. So here we have this thing. If you think about either the level structure or the graded structure or certainly the composition structure on symmetric sequences, this does not preserve arity. What we need to have is some sort of monoidal structure on symmetric sequences for which this preserves arity in some sense. So that's what's going to motivate us, what we need to put in the place of those two question marks. So this is what Bill and I call the matrix monoidal structure on symmetric sequences. So this is going to be a structure for which this operation is arity preserving, homogeneous but arity 0. So this is going to be a symmetric monoidal structure, which we call box, because there's so many other signs that are already used for other things. And also because matrices tend to be boxy. So what is it going to do? So it's going to take a pair of symmetric sequences, x and y, to x box y, where x box y in arity n is a disjoint union over all k and l such that k times l is equal to n instead of k plus l or anything else. xk cross yl cross, and here's something I'm going to have to explain, sigma k cross sigma l, that's unreadable, and then sigma n. Where the trick here is that how are we looking at sigma k cross sigma l as a subgroup of sigma n? We're thinking about n as sigma n not as being the permutation of numbers from 1 to n, but as permutations of pairs ij, for I between 1 and k, and j between 1 and l. And so sigma k here is acting by permuting lines, and sigma l is acting by permuting columns, which is another reason why we call this matrix monoidal structure. So we have this permuting lines and permuting columns that's going on. Okay. So this gives us a nice symmetric monoidal structure. In fact, it's coming from a Day convolution. Convolution just on given by multiplying. And since this is coming from Day convolution, we know by abstract categorical magic this is actually a closed monoidal structure. But in fact, it's interesting to know how it's a closed structure. So how is the closed structure? Is the following way. So for any symmetric sequence y, we have an adjoint pair between boxing with y and looking at the following thing, so let me try this properly. So we look at the sigma equivariant maps from y into some construction that I call gamma dot. Yeah. And this gamma dot is actually interesting. Gamma dot is some collection of functors. Gamma n is a functor from symmetric sequences to symmetric sequences, such that if I apply gamma n to, let's say, x, in arity k, it's x in arity n times k, so you're going to have this multiplicative thing coming on, and then I pull this back to looking at it as something over. Okay. So this is. So this is the permuting lines.
You mean NK?
NK, sorry, yes, thank you. Okay, so that just it just sort of do the obvious thing here. And so you have this collection of functors, you have a very explicit description of what this right adjoint to taking the tensor product with any object looks like. Okay. So now I want to say something about certain important properties of this box product. That we'll use then in order to define the structure that we need. So we have a second lemma. It's one of these things that you could call a lemma only because maybe it's more interesting for what you use it for than sort of in and of itself. It's one of those lemmas that has a proof longer than the theorem in the paper, but that there exists something that a sort of associative, in some appropriate sense, natural transformation from, it's called sigma. So I could take, if I have 4 symmetric sequences, I can first take their composition product, then box, then composition. And this is one of these things where you can sort of pull W through X, and you have something that looks like this. There's a nice sort of associative in an appropriate sense, natural transformation here. Now, I think Bruno, for example, has thought about things that are sort of two-monoidal. So I think that one can actually go farther than this, not prove that this is just a natural transformation, but I think this actually endows the category of symmetric sequences with a two-monoidal structure, if you ever needed something like that. But we don't need the full power of that, so we just stop there. So there's that, and then once you have that, this is where it comes into play. This is the tool that we need in order to define this. Oh, I should have said. Right. I mean, the whole point of defining this matrix monoidal product, if I go back to the question marks here, is that what we're going to want to do is replace this with the box product of these two guys. So that's where this is going to come in. But we're not there yet. Because what we need now, in order to do that, is this next lemma, which says that these are just any symmetric sequences. There were no particular algebraic structure. But if we now have some operads, then in fact, there exists a natural transformation continuing alphabetically through the list, we'll call it tau, that takes somebody who looks suspiciously like a free PQ bimodule, somebody else who looks suspiciously like a free P prime Q prime bimodule, and then takes it to something that looks like a free P tensor P prime Q tensor Q prime bimodule. And this natural transformation is supposed to be appropriately compatible, and I'm not going to do the diagram for you. It's the, let's see, who was saying yesterday the obvious relations? So I'm going to invoke obvious relations, obvious compatibility that is compatible with operad multiplication. And I'm running a bit short on time, so I'm not going to do the construction, but it's not too hard to see how to build this thing from lemma 2, and then from this operation here that goes from P cross Q into P tensor Q. Use that operation and use lemma 2. You can probably figure out how to make this natural transformation tau. Okay. So once we have that, now we're ready, finally, to construct this lifted tensor product. Whoa. So this is the third step in the process. Okay, so the key to the whole story is like what de Ruytenberg was saying yesterday, that, well, you know, any algebra is a co-equalizer of free algebras, and so all we really need to do is figure out how to do the free case. So key every PQ bimodule is a co-equalizer free bimodules. So it's enough to do the free case. Okay, that's a shortcut. There's a little bit of work to do to show that that's really enough, but it really is. So let's do what we want to do. So we're going to set fpqx tensor tilde f p prime q prime x prime. We're just going to say, okay, we're going to let that be equal to what we want it to be. And see whether we can make that work. Because on objects, okay, it's no problem. Now the question is, what about morphisms? So we need some sort of naturality. And this is where this natural transformation tau is going to come into play. So suppose that I have two morphisms of free bimodules. So A from fpqx to the free bimodule on some y, and say A prime, the same thing but with primes everywhere. Oh, sorry. Okay, so let's play a little categorical game. So we know that this morphism of free bimodules is determined by its restriction to the generators. So let's call that restriction to the generator is A sharp. So now I'm forgetting the bimodule structure. This, and here I have A prime sharp. Just a morphism of symmetric sequences. Okay, and what I want to be able to do is take these two modules, these two morphisms of free bimodules, and build from these two morphisms of free bimodules, one from the free P tensor P prime, Q tensor Q prime on X box X prime to the tensor product of these. So how am I going to do that? In order to do that, I have to define a morphism of symmetric sequences from X box X prime into the appropriate target, which is the Y here. Okay, so we do that in the following way. Here's X box X prime, which maps by A sharp box A prime sharp into these guys. And now we use our magic transformation tau to finish the story. P tensor P prime Q tensor P prime. So this is a morphism of symmetric sequences, and then we can apply the adjunction again, and that gives us, I'll put it over here, the morphism of bimodules that we wanted. So that when you're trying to define this kind of construction, you know what you want it to be in the free case. The important thing is then to figure out what happens in the case of morphisms. And now, so this is going to give us the thing we'll call A tensor tilde A prime will be given by taking this composite and then adjointing it back. Q prime X box X prime to the free thing on Y box Y prime. And you can show that when you do that, you end up with something that actually has an associative composition. Everything works out as it should. Okay. So that's really the end of the proof of the main theorem. That one can go through it like this. One can say what one wants for it to be on the free ones. You can show that you end up with naturality on the free ones, and then play the co-equalizer game to define it everywhere. Okay. So two further properties. The first one is really just a lemma again. And this one really is a lemma. It's not hard to prove at all. I guess I'm up to 4 or something. Which is that, so we have this functor gamma n from symmetric sequences, symmetric sequences. It was this thing that takes a symmetric sequence and it gives you something in arity n, which was arity k times n before. So it turns out that gamma n, which is this endofunctor on symmetric sequences, restricts and co-restricts to an endofunctor of PQ bimodules for any P and Q. So it behaves really nicely. It gives you the structure on PQ bimodules. And the reason you care about that is it tells you that this lifted Boardman-Vogt tensor product also has a nice right adjoint. This is the last thing I'm going to say, Ezra. So that this proposition makes sense. So proposition. So for any operads P, P prime, Q, Q, Q prime, and if I take any M prime, which is a PQ bimodule, we have an adjoint pair given by tensoring with M prime that goes from PQ bimodules into P tensor P prime, Q tensor Q prime bimodules. Like this. And the right adjoint, let's call it R there. So R uses our gamma again. So it's map over, let's see, I'm going to get this wrong if I don't look. Taking into account the P prime Q prime structure from M prime into, again, uses gamma dot. So the reason we need this lemma is so that when we apply this guy to P tensor P prime, Q tensor Q prime bimodule, it still has the same structure. And so it makes sense to take mapping space with respect to that. And it gives us an adjunction like this. So that's the end of sort of the theory of these things that I wanted to discuss today. I'll just say briefly that this gamma n comes up in the other application of these structures, because putting together some work that Bill and I have done on derived mapping spaces for operad maps, and some work of Dev Sinha, Gregor Rohn and Victor Turchin, Brian Munson, and Ismar Volic, putting together a lot of people's work, we can prove that there is an interesting fiber sequence where the middle term is a space of long links, and the fiber is a double loop space on a certain derived mapping space of operad maps. But the operad that we get is built actually by applying this gamma n to the little n-balls operad. So this gamma n comes into this construction of this model for the long link space. But that's the end of the story for today. Thank you.
Definitely a talk on operads. Questions?
So just a quick question. So if I have a bimodule between two rings, I can think of this as a generalized homomorphism between the two rings, right? So if I take as Q the endomorphism operad of a vector space, I can think of a PQ bimodule as a generalized P algebra in some sense.
Mm-hmm.
Can I try to generalize commutative algebras, associative algebras in that way and extend things like cyclic homology or whatever to a larger class of objects?
I would expect so. I haven't thought about it, but I would expect that we could do something like that. I mean, the way that we figured out what to do here was really thinking about what really is going on in the case of bimodules over rings. Because when you're working with bimodules over rings, all of the tensor products inside are the same. So it's a little bit hard to see what it is you're really doing when you define the tensor product with bimodules over two different pairs of rings. When you sort that out, you see that actually you are playing exactly this kind of a game. It's not so clear. I mean, it's very easy to do. You don't have to think about what you're doing. But if you do start thinking about it, I actually have to think about all these tensor products as living in different worlds. But they all actually turn out to be different tensor products in this context.
So you described what happens with the tensor product of right modules.
Uh-huh.
What if I have left modules? What is the Boardman-Vogt tensor product of them there? So if I have for instance, two algebras,
right.
one EM algebra, one EN algebra, what do you get?
Haven't thought about it. I don't know. So you're going to get something that is going to be an EM plus N algebra, but how it compares, I don't know. It's a very good question.
One of the other relations to this factorizationology stuff is that, one way of expressing it is as a pairing of a left module and a right module over the operad. It's the relative composition product over the EN operad of the right module you wrote down associated to the manifold and the left module given by an algebra in degree 0.
Right.
So if you knew the answer to that question, my next question would be, whether the relative composition product distributes in some way over this. I don't know.
I would think so. I mean, I would love it if you wanted to do that.
Yeah, Bruno. So now we have a lot of products or S modules. We have the RTY tensor product, the tensor product, the Lamar product, the box product. So all these was satisfying.
The relations among them?
Yeah, so you just need these for your purpose. You just need this one, this limit 2,
right,
between circle and box.
Right. That's all that I need.
But then,
But
yeah.
There's certainly, I mean, I thought about, I mean, it's written down in my notes somewhere, some relations among them, but haven't, I only have what I need so far. But I think there are probably definitely some interesting relationships among all these products. And this matrix one comes up very, very naturally, and it's very cool.
Yeah. Have you thought about what happens on homology of modules?
That is to say,
if you know the homology of M and you know the homology of N, can you work out the homology of the tensor product?
There should be some spectral sequence, certainly, because I mean you can do kind of the natural filtration coming from the way this thing is defined. So there should be, but it'd be yeah. I have to think about it. I haven't.
Do you have a quick question?
Yeah.
It's related to some of the previous questions. So your tensor product satisfies all sorts of distributive laws. However, let's say, well, instead of operads, if you have rings, right, and if you have a PQ bimodule and a QR bimodule, you tensor them together to get a PR bimodule.
Right. That's right.
Do you have anything of that kind?
Right. So I bet that works nicely because of this lemma 3, because the fact you can sort of pull these things together. So I have to think, I have not thought about it, but I suspect that it does distribute nicely with respect to tensor group. But I should think about that. I haven't.
Okay, let's thank the speaker again.